This is our introduction for lab next week since we have a test this week. So we're going to complete our synthesis of a chemiluminescent product. Remember last week we made this large conjugated molecule that was fluorescent. Right, so we made it and we tested it. We shined UV light on it, right, as a photon. And then we got off a photon of lower energy blue light that we could see in the visible range, right? So we had made this product and tested it using a Wittig reaction. And so we kept it for this coming week for the lab, right? Now we want to excite it. Instead of exciting it with light, we want to chemically excite it to make it give off light. So we're going to chemically excite it instead of spectroscopically excite it. Okay, so in order to do that, we've got to do a synthesis of a different molecule. So the molecule we're going to synthesize is this bis 2,4,6 trichlorophenyl. So bis differs from di in that bis means the two groups are connected to different places. We have two large groups connected in different places, so it's a bis. If this is 1, there's a chloro on 2, 4, and 6 of each ring. So trichlorophenyl. And if you remember from naming carboxylic acids in the carboxylic acids chapter, the 2-carbon dicarboxylic acid is oxalic acid. And so this is an ester on both sides of oxalic acid. So we take off the, right, if we start with the name oxalic acid, right, you take off the ic acid and replace it with ate as part of naming the ester. So this is a diester of oxalic acid. And so we're going to start with our source of, our alcohol-like source, in this case a phenol, right? 2,4,6 trichlorophenol, right? Remember, phenol is the aromatic hydroxyl compound. They're similar to alcohols, but more acidic. And so that makes it easier to turn this into a nucleophile. It's easier to deprotonate. And then we're going to have oxalyl chloride. So this would be classified as a diacid chloride. So that fits with the chapter that we're talking about, the chapter on acid derivatives. So this is an acid chloride. Note, right, you have an acid chloride group here and an acid chloride group there. We're going to use triethylamine as a base to help deprotonate our phenol to turn it into a nucleophile. So we have to be careful, right? These kinds of halogenated phenols are suspected carcinogens. So, handle them carefully, use gloves. Oxalyl chloride is very corrosive. So it will act on metals, but it's also a lacrimator, which means it will, if you breathe the vapors, it will attack your mucous membranes and make them make mucus and tears. And so in this way, it's similar to tear gas, right? In that it attacks your mucous membranes and makes them make more fluid and mucus. So make sure you keep this in the hood. And again, triethylamines. Amines are known for smelling, for having bad smells. So keep the triethylamine in the hood. So we will make our product. Our byproduct is going to be triethyl ammonium chloride. Okay? So here's the mechanism of the substitution. All right, let's go that way. Let's make this just a teeny bit smaller. Okay, so our triethylamine acting as a base deprotonates our phenol, right? That's going to leave it deprotonated and nucleophilic, right? It may not be shown, but that oxygen has unshared pairs of electrons and would be a good nucleophile, right? Then, and this is characteristic of an important reaction in the chapter we're covering, right? This is an example of a nucleophilic acyl substitution. Nucleophilic acyl substitutions are very common reactions, and they are important in biochemical processes. So in a nucleophilic acyl substitution, it occurs in two steps. So the nucleophile attacks the carbon of the carbonyl of the acid chloride in this case. And when that happens, the pi bond opens up to form a sigma bond, and you get a tetrahedral intermediate. So that tetrahedral intermediate is characteristic of the nucleophilic acyl substitution mechanism, right? So you can't skip the tetrahedral intermediate. It's not one step like a nucleophilic substitution on an sp3 hybridized carbon. You get that open up to form the tetrahedral intermediate. There's lots of evidence that that intermediate exists. And then the electrons from the oxygen flow back to that carbon, because there are two electronegative groups on it. Here there are three electronegative groups, 1, 2, 3. So this carbon is a center of positive charge. So the electrons flow back, and now that's going to give this carbon too many electrons. It has to let something go. So the best leaving group of the group is the chloride ion, so it takes the electrons and leave. I apologize for that poor form of my arrow touching the atom. I could have done it with a different arrow so that it didn't touch. But once it does that, now we have created our new ester bond. Right, there's our new ester bond. Let's do that a little better. Right, there's our new ester bond. And now we've got, on the other end, right, we've got another one, right, another acid chloride group ready to do it again. So the second step is to repeat with the trichlorophenol, with another trichlorophenol. So just do it again, right? And then you will get your final product. Okay, so here is that product, the bis 2,4,6 trichlorophenyl oxalate, right? Our product with two ester groups, right? There's There's one attached, right? There's our other ester, right? So it is a diester. So the next step of the reaction, we have to create a high-energy molecule that will excite our fluorescent compound, right? So we're going to react that product. We'll create it and isolate it, and then we'll react it with hydrogen peroxide in a diethyl phthalate solvent, right? It's a fairly high boiling solvent, okay? So we'll react with hydrogen peroxide, and the hydrogen peroxide attacks one of the ester bonds, and I'll show you the mechanism on the next slide, and creates a peroxyoxalic acid ester, right? It's a peroxyoxalic acid ester, right? Because, right, this ester bond is still there, right? So the hydrogen peroxide attacks one bond, so you get an intermediate, which is a peroxyoxalic acid ester. But then that can come around and attack the other bond, right? So it attacks the other ester bond to create this highly strained intermediate, this 1,2 dioxetane dione. Okay? And so this product is, has high angle strain, right, which makes it high energy, right? You have an oxygen-oxygen bond, which tends to want to undergo homolytic dissociation, right? That's very favorable, which also increases the energy, right? And there's a lot of electronegative groups in one small spot, all of which contribute to the energy of that molecule. And so now what we want to do is link the decomposition of this intermediate that we're creating in the reaction mixture and allow that energy to be transferred to our fluorescer, our trans 9,2-phenylethanol that we made last week. And in the same way that the UV light excited it and then had it emit visible light, in fluorescence, we want our reactive molecule, right, our dioxetane dione, to transfer energy to this molecule. And since we're transferring it chemically, right, this should just spontaneously take that energy and turn it into visible light. That's our goal. So here is a mechanism for the reaction of our oxalate diester with hydrogen peroxide. So if we start here, right? So our hydrogen peroxide, right? Again, we're going to do a nucleophilic acyl substitution, right? So we're going to follow that same pattern. So our nucleophile attacks, pi electrons move to the oxygen to open that up, create a tetrahedral carbon in the intermediate, right? So we have a tetrahedral carbon on the product side. And then I drew it as a concerted reaction, but if we want to follow along, we could talk about a transfer this way. We could simplify it by saying this oxygen can take that hydrogen ion and allow these electrons to go back to the oxygen. Right? That's going to make this oxygen positive now and make our phenol a better leaving group. So now if we move to the next step, right, when the electrons from the oxygen flow back to recreate the pi bond, now that oxygen is protonated and ready to leave. And so you could do that in 2 steps instead of one as a concerted reaction the way I did it. But you can see here on the product side, we have broken our ester bond. This whole phenol, which is a stable molecule, is free to leave. As I look at it, I see that we are missing the 2 electrons there, right? So it is free to leave, right? And now we've got our acid peroxide, our peroxy acid group on this side, and our ester group on this side. So our next challenge is react our peroxy acid with our ester. Okay? So it would be strained, but if our oxygen from our peroxy acid side can attack the other carbonyl, again, nucleophilic acyl substitution, opens up, creates tetrahedral carbon intermediate. Again, if you want to think about it stepwise, oxygen takes hydrogen ion, making this oxygen now positive, right? This oxygen is now positive, and so it's a better leaving group. So in the second part then, as electrons flow back from the negative oxygen to recreate the pi bond, this oxygen, which is already protonated, can leave. Now we have broken our second ester bond, right? Another trichlorophenol can act as leaving group. Again, somehow, let's make it, right? Missing the unshared paired of electrons, and we have created our high energy product ready to decompose and excite our fluorescer. Okay? So, the procedure, again, this is a procedure that was put together by Dr. Stickney. It's not in the lab text, right? So, a couple of points. We don't need a lot of the fluorescer, right? No more than 50 milligrams. If you have less, the reaction will probably work, right? We're going to use the analytical balance, right, to get enough significant figures for the small amount we're using, right? So it's not going to take a lot of the bis 2,4,6 trichlorophenyl oxalate, and then about 3 milligrams of your fluorescer, right? So 3 milligrams is 0.003 grams. Right? Right? We'll warm them on a steam bath, right? We're going to use 30% hydrogen peroxide here. Now remember, hydrogen peroxide, right? This is not drugstore hydrogen peroxide. This is a strong oxidizer, right? And so you have to handle it carefully. Use your gloves, right? And then remember, we're going to use diethyl phthalate. That's our solvent for this reaction, right? So our reaction will be in about 5 milliliters. So you're going to put the peroxide into the diethyl phthalate. Then you're going to add that suspension dropwise to the solution of the oxalate ester with the fluorescer. And this is the thing, when you do this, you want to be in the dark. And as you do it, we hope you see a glow, like a glow stick. Note the color, right? Because different fluorescers will produce different colors. And then once you get a glow, you can play with it, right? You can heat it, right? You can put it in hot water to see what happens. You can put it on ice to see what happens, right? And so in each case, right, note that in your observations in your lab notebook, okay? And so at this point, you can start to experiment a little. You can add a little more of your product from last week if you've got it. You can add a little more hydrogen peroxide, especially when the color starts to fade. So, right at this stage, you can play with it a little bit and see what happens. Just make a note of each observation in your lab notebook. So I hope this helps you get ready for lab next week. If you have any questions, please see me or please see Dr. Stickney.